Alright, so today's video is going to be on LO 2-6, which is that students should be able to identify force pairs between objects in a system. This video is focusing on Newton's third law, which in junior high school you would have learned as this statement right here: every action has an equal and opposite reaction. But I really don't like that definition, and the part I don't like about that definition is this word, reaction. It makes it seem like what Newton was saying there is that first one thing happens and then another thing happens. So to look down at this example right here, people often think that action and reaction means something like this guy said something mean about me, and so I punched him, right? This was the action, and that was my reaction. Now, ignoring the fact that that's an inappropriate reaction when people say words to you, that also is not what Newton was talking about when he was writing Newton's third law. What Newton was talking about was a little more complex in a way. And so we're going to have to be careful in trying to understand it. So what Newton was saying was that every force is an interaction. So there's always two objects involved in a force, and they're doing something to each other. It's not just a one-way sort of relationship. And so what we know about that interaction is that when object A, which is here in purple, applies a force to object B applies the equal amount of force back to object A. And we call this a force pair. So if we look at this bumper car example, we're saying that this object right here is object A, that red bumper car, and this object right here is object B, the blue bumper car. And we know that when they hit each other, object A is going to apply a force onto object B. And we see that force right here. So there's an applied force from object A, that's where it started, to object B, and that force is to the right, okay? So that is the first force in the force pair. The other side of this force pair is that when object A hits object B also hits object A. If you've ever been in bumper cars, you've experienced this. When you run into your friend, you see them feel the impact. You know, their body gets knocked around. But when you hit them, you also feel the impact and your body gets hit around, gets knocked around. Assuming your bumper cars are roughly equal size and both people are roughly equal size, then the experience of those two people is actually exactly the same experience. And as we'll talk about right here, the forces are also exactly equal. So we have another applied force over here from object B on object A. This one is to the left. And you'll notice these two forces are exactly equal. Okay, they're just in opposite direction. All right, let's look at this example over here. So we've got the Hulk. This is a classic superhero movie mistake. We've got the Hulk grabbing a helicopter, and usually in the movie they grab the helicopter and they pull really hard and keep it from flying away. That was actually Captain America in the Avengers, but I couldn't draw Captain America in a way that you would recognize him, so we went with the Hulk. I've got here a force of tension drawn in purple, and that is the pull from object B, which is the Hulk, onto object A, and the Hulk is pulling the helicopter down. Now here's the thing these movies forget. This is a force pair. So if the Hulk pulls the helicopter has to pull on the Hulk. And the helicopter is going to pull with the same type of force, a tension, in the opposite direction, and it's going to be the exact same amount of force. So unless there's something holding the Hulk down, the helicopter's still going to fly away, just with the Hulk holding on. Because it's not just the Hulk pulling that matters, the helicopter is also pulling back. Okay, and that's what we mean when we talk about a force as an interaction. The two objects are pulling on each other. Okay? And as I said earlier, when we're comparing the forces in a force pair, we want to repeat again and again and again that both forces of a force pair are always equal. There's a lot of really fundamental laws of the universe that make that have to be true. But for right now, just know that it is. Now, just because the forces are equal, and this is where people get confused, that does not mean that the effect of the forces is equal. So I want to use this example really quick. So right here, we've got an applied force from a fist on a face. Okay, and so the fist is hitting the face to the right. If that's true, if the fist is hitting the face, the other force in that force pair is an applied force from the face on the fist. I just want to show you a quick trick for how to identify force pairs. If I ever ask you, what is the other force in this force pair? And you can think, well, it's the force we're talking about is an applied force from a fist on a face. To find the other force, all you do is take the same kind of force, so it's still applied, but you swap the objects. So over here, still the same kind of force, face and fist have been swapped. Okay? So that applied force from the face on the fist is in the opposite direction, and it's just as big of a force. Those two forces are equal, but the effect is not the same. And the effect is not the same for a couple reasons. One, the hand is wearing a glove, and the glove protects the hand from being broken or being seriously injured, so the person punching doesn't break their hand. That is what boxing gloves are for. They are not to protect the person's face, because the point of boxing is to hurt the person's face. So why would you protect it? On the other hand, faces get more injured also because they contain squishy little brains inside, and squishy brains are easy to damage. So one of the reasons that the effect might be different is because the objects are just different materials, not because the forces are different. Okay, what about this? Got a baseball and a baseball bat. Well, we know that there is going to be a force applied from the bat on the ball, and that force is going to point this way to the left. The other force in the force pair is then going to be an applied force from the ball on the bat, and that force is going to be equally strong in the opposite direction. Okay, so those are our two forces in the force pair. Those forces are equal. The bat and the ball experience the same force, but these two objects have different masses. And since they have different masses, they will have different accelerations, especially when we consider the fact that this bat is being held by a person, and that in many ways that person's mass is also connected to the acceleration of the bat. And we can see why this is true by looking at Newton's second law. So Newton's second law, force equals mass times acceleration. So if the ball right here has a very small mass, then it's going to have a very large acceleration because these are inversely proportional, and the ball is going to go flying way down the field. The bat, on the other hand, has a very relatively large mass, and so the bat has a relatively small acceleration. Okay, so one of the reasons that things might experience different accelerations in a collision is their mass, not that they have different forces. Notice the forces are still equal. Okay, another thing that might happen is there might be other forces like friction that we need to think about. The force pair are not the only forces on an object. Okay, so we've got this horse and this carriage, and the horse is pulling on the carriage with a force of tension, which we're drawing right here. So the horse is pulling this way. I'm going to write it as F10's horse on cart. I call it a cart because that's shorter to write. And the other force then, again, remember, switch the objects, is a tension force to the left from the cart on the horse. This might seem silly, but if you've ever pulled something heavy, you know that you can feel the weight dragging you back. And that's exactly what's happening to this horse. And if you look at just this, you would think, oh, those cancel out and we're not going anywhere. But they don't cancel out. And the reason they don't cancel out is, first of all, this is a force on the horse, and that is a force on the cart. And so they cannot cancel because they're not on the same objects. Another reason is there are other forces involved that we might not think about. So if the force of friction between the horse and their hooves, like right here, the horse is pushing their hooves back and friction is pushing forward. That's why friction is pushing forward on this horse. And if the force of friction on the cart is equal to the force of friction on the horse, guess what? You're not going anywhere. But the force of friction on the cart is not equal. The cart has wheels, so it's going to have very little friction. And that difference in friction means that the whole system accelerates to the right. Okay, so it's going to have a net force to the right. Not because the force pair is unequal, but because another force is unequal. Okay, now let's talk about some things that are not force pairs. All right, so looking at this car, there's an applied force to the right and a force of friction to the left. And a lot of people will say, oh, great, those are a force pair. They're in opposite directions, and they might be equal. They are not a force pair. First of all, because they don't have to be equal. The applied force can be bigger than the friction can be bigger than the applied force. But how do I ultimately know these are not force pairs? Simple. Force pairs are on different objects. These two forces are on the same object. They're both on the car. And if you think about what we did for every other example, we had like applied force of bat on ball, applied force of ball on bat, applied force of fist on face, applied force of face on fist. Every time we had two objects interacting, and each force was on a different object. This is not an interaction. And so these are not force pairs. Okay, what about this one? We've got gravity pulling down on this weight and tension pulling up. Now they do point in different directions. They might be equal, But again, they're on the same object. And since they're on the same object, they cannot be a force pair. Okay? What is the force pair, you might ask? What if you have to figure out what is the other force in these pairs? Well, this is a tension. Sorry about that. This is a tension from the string on the mass. And so the other force in that force pair is a downward force of tension. Remember, it has to be the same type from the mass on the string. Okay, that is a force pair. If you think about gravity, what is the other force in the force pair for gravity? Well, this is gravity from the Earth pulling down on the mass. So the other force, same type, equal amount, opposite direction, is the force of gravity from the mass pulling up on the Earth.